Good morning, everybody. It's my pleasure to introduce Professor Dan Roth for this morning's distinguished colloquium. Professor Roth is Chief AI Scientist at Oracle and Distinguished Professor of Computer and Information Science at the University of Pennsylvania. He's a fellow of ACL, AAAI, ACM, and AAAS, and the recipient of the John McCarthy Award. For those of us who have been following his research for many years, it's really unique because of the way it combines machine learning with computational and linguistic insights. Dan has always been able to capture more of the structure of language and machine learning methods than just about anyone else, and has the performance and impact to show what that brings. I'm excited to hear about reasoning in light of the dramatic changes in the field from Dan's perspective. Okay.
Thanks a lot, Matthew, and thanks a lot for coming and being on the Zoom here. So I'm going to be stuck here because I don't have a detail, so I will not be able to move too much. And yeah, I want to talk about, what the title says, language models, believe it or not. So, I mean, we are all interested in this today. AI is in the news, and people are talking about, have we solved it all? Have we reached AGI already? When is it coming? And, everyone started to be really excited. And AI has become keyword following ChatGPT appearance a couple of years ago. But now all the major players are playing in this game, and a few non-major players are also playing in this game. But at the same time, there are many, many problems that we are all aware of. So we've all seen these problems of, ChatGPT invented sexual harassment scandal and named the real professor as the excused, and many, many other things that some companies have already started to pay money for this, and some funny cases. But the bottom line is that we call these hallucinations, but it has to be clear that these are not due to some wrong reading for the most part that models have done, but really a reflection of models making wrong decisions. And there are many, many other wrong decisions that models are making all the time that did not make the news yet. So really, where are we? Everybody is excited about large language models, and then there are good reasons to be excited about it. But it's really important from my perspective to make sure that we are not misinterpreting this technology, because understanding the technology is key to deal with the risk, the limitation, and benefits of this technology. And also from our perspective here, where should we focus the R&D effort that we have? So I think that we should not think about AGI. AGI is not coming, but we should think about this new technology as really a good technology that allow us to advance assistive technology. And what really think about language model as the new UX. And what I want to do today is mostly give a perspective on where we are in this space. And I'm going to sprinkle this perspective with research results, mostly from my group at Penn, that I think shed some light on these things. And I want to start with two disclaimers. First of all, I'm using example for multiple companies, and I don't want you to take this as criticism of specific models or companies. It's really part of the discussion. And my goal is to just shed more light on the state of the technology. The second disclaimer is that I'm going to give a lot of examples, some things that were incorrect, a couple of weeks ago, models can do today and vice versa. But this still reflects where the technology is. So I want to start by showing you this slide that basically shows results of multiple models over a range of benchmarks. And what's interesting here is on the left side, On the right side, I put tasks that are mostly memorization focused. And on the right side, these are tasks that are mostly decision-making or reasoning focused. And you can see that while on the right side, we are doing quite well, on the left side, the average results is something like 60%. And where we really need it to be, if we want to support decision-making consistently and reliably, we want it to be on close to 100%. So this is where the challenge is. This is where research should focus. I want to go back to the history. There isn't a lot of history, but the short history of large language models. And I think ChatGPT came to most of our consciousness a couple of years ago in a conversation that Kevin Roth, the tech journalist of New York Times, had with ChatGPT through Bing. And this was a very long conversation. I'm going to zoom here so you can read a part of it, and you can be hopefully impressed with the level of fluency that the model has shown and the knowledge that the model has shown. I mean, this is really, really impressive. Clearly, the model knew a lot, and clearly the model can produce good English. Is it smart? I don't know. I mean, at the end of the conversation, the model asked Kevin whether he wants to leave his wife and move in with it. But really, this is really important for us to understand, and this brings the first lesson that I want to highlight. What we've learned from this and other observation is that being linguistically coherent is much easier than we thought. You take a deep model, a very deep model, train on trillions of tokens to predict the next token, simplistic way of training it, and you can generate very coherent text. Now, we were trained all our life to equate being linguistically coherent with being very smart. And I think that we are projecting this to the current conversational models. I don't think this is the case. And before I'm trying to kind of move on and show this, I just want to make sure that we understand what do we mean by training over trillions of tokens. So an average book, 200 pages book, is about 100K tokens. So a trillion tokens is about 10 million books. And all the models today are being trained on multiples of them. So models have seen tens of thousands, tens of millions of books. How many books have you read? And you know, if you are an avid reader and you're reading a book a week, you read all the time, you read blogs, you read everything, you will probably read in your lifetime or active lifetime something like 3,000 books. And this is one reason why we are so impressed. The models know everything. They have read everything. And you know, including all the, you know, standardized tests. They've seen these many, many times. And they just know. And we as people that know nothing, basically, we are very impressed that the models know things that we think you have to be very, very smart. But really, they read it, and they know how to access it. And this is not a simple thing, very easily and relatively reliable, and can generate text based on it. So in this talk, I would like to argue that, you know, the models are good, but they will not solve all the world's problems. But they will be very useful assistive technology. I'd argue that models cannot reason, nor can they make decisions consistently and reliably. And we are basically misled by what I call the token bias and memorization abilities of the model. But there's still a lot of things that we can use these models for, and even these are challenging. And some of the key challenging are how to go outside the model and basically orchestrate other models and other tools and do useful things. So let me start with one of the things that I think really is unique about this new technology. Because if you think about it, for old machine learning, we really had to train models to do one task at a time and train them for this specific task. One of the cool things about language models, today's technology, is that they can follow instructions. So you don't need to train them for one task. You can give instruction, do this task. And they kind of understand what you want and follow this. So how do we evaluate this? And how good this is? So this is an experiment that was published last year in NACL that attempts to develop some methodologies for evaluating instruction following in a good way. And the game we're playing here is in the domain of question answering. So you start with a question, for example, like Athens emerges as dominant economic power in Greece around the late 6th century BCE, and so on. And then you ask a question like, when did Athens emerge as an economic power? And we're taking this collection that we know the models are doing well on, and we are perturbing them into ways. On the top perturbation, we're taking questions that the model can answer correctly, both open and closed book. And we are basically replacing the answer. So in this case, instead of in the context saying 6th century, I'm going to change it to 4th century. So what I've done here, because I know that the model can solve these problems, both open and closed book, I've generated conflict between the parametric knowledge of the model and the context that I'm giving the model, and I'm asking the model, look at this context and answer accordingly. So that's one change that we're making. The second one is I'm taking the collection of questions where the questions are open book correct, which means I know that the model can follow the instructions, but closed book wrong. So it's likely that the model doesn't have this information in its parametric knowledge. And in this case, I'm just taking the context on which I know the model was able to answer correctly, and I'm enriching it a little bit. So basically, I'm adding another paragraph that is relevant to the context, but doesn't change the truth value of the answer. So basically, these are the two changes that we're making, basically challenging the instruction following capabilities of the model. And this is what we see. For the first one, the top one, which we called answer swapping on the left, and the right one, which I called context enriching on the right, you can see results. I compare it to what is here Amazon Telker. These are humans that basically are asked to evaluate this. And all of us that have played with these tools and hired Amazon Telkers know that they are not perfect, but they're humans, they know what they are doing. And in this case, they are doing sub 10% mistakes. But all the models, including the top ones, are making between 20 up to 50% mistakes on these scenarios, which means that actually maybe we are not as good, or the models are not as good as we think. So maybe understanding, which is required here, is a little bit harder than generation. Maybe the way we evaluate generation is too lenient, because we just look at the output and we see something correct here and we say, oh, yeah, the model is good. And we don't necessarily read it very carefully to see that some parts of the answers are hallucinations or just incorrect. So with this as background, I want to move to what I really want to talk about, which is reasoning. So what is reasoning? I'm not going to define reasoning. I mean, there used to be good definitions in AI for reasoning 20, 30 years ago. These no longer are relevant because we call too many things reasoning. To me, reasoning is really a process that has a unique answer that can be derived or proved via a formal system. But we don't need to leave it at that for most of the discussion that I'm going to have. I'm going to start with spatial reasoning. So here is an example of spatial reasoning problem. I'm going to zoom in so you can read it. So this is the challenge. The cup, I'm going to give some text to the model. The cup is on the right of the plate, the spoon is on the left of the plate, the knife is in front of the spoon, and so on. What's the relation between the knife and the saucer? So if I was giving it to you or to any 5-year-old, they would basically take a piece of paper and would place the knife here and the spoon here and the saucer here, and then we look at it and they say, oh, that's the relation between the knife and the saucer. Models don't do this. They just read the text. Lo and behold, I mean, the model actually, GPT-4 gets this. And we are very, very impressed. Why does it get it? I think that this is a token bias because the model has seen thousands of cases where A is to the left of B, B is in front of C, C is to the right of D, and they kind of know what the relation should be. But if you try to quantify this, and it's very easy to quantify this kind of task, you can invent multiple objects. I'm going to call them in this slide, D, B, G, J, and F. You can invent a story about the relation between these objects. And then you will choose 2 random objects and ask what's the relation between them. And when you try to quantify it, you see that the models solve between 25 and 45% of these cases, which is still impressive. I mean, why would they be able to do it at all? But But this is not enough. I mean, we cannot live with reasoning modules that solve, just a small fraction of the cases. And this is true even for very simple spatial reasoning problems. It is a simple one. Ellen, Bob, Colin, Dave, and Emily are standing in a circle. Ellen is on Bob's immediate left. And then the question, who is on Ellen's immediate right? And I know that you know the answer, because it's a very easy question, but here is an answer from GPT-4o that gives a lot of story and explanation and so on, but it's wrong. And this happens to a lot of cases. It's been quantified a range of similar problems like this. Models do not get right or do not get right consistently. We can move to quantitative reasoning, but all of you have seen that models cannot do this. I just want to give you some statistics so you'll be impressed. So this is a collection of results on 4 operations in the range of 10 to the minus 5, 10 to the 5 by multiple models. And you can see that models are pretty bad. And it's not surprising, right? And really, we don't want to train models to do this because we have calculators. But really, it has implications on a lot of decision making that we want models to do, specifically tabular, using tabular data and so on. So we have to kind of be aware of it. And in this community, I probably don't need to talk a lot about how models are being trained and work, but really, it's a very simple, conceptually, pre-training method. You hide part of the input and you try to guess it only. So it's really a supervised classification task. This is how we train the models. And depending on the architecture, whether it's encoder, decoder, or decoder only models, we're doing it slightly differently. But the key thing, and I think the key excitement that came to the community is because of this idea of self-supervision, because people said, oh, in old machine learning, we had to annotate data, and we had to pay a lot of money, and we couldn't collect a lot of data in order to train models. And now, we just stream in text, and we do this self-supervision. The training itself is supervised, but now it's cheap. We can use any data that exists, and this is exciting, but it's not all. Because most of the effort today, over the last few years already, in training is not only in the pre-training stage, but rather in the SFT stages and in the RLHF stages that are very, very expensive because they involve the model itself in the loop. But at the end, the bottom line is that this is a feed-forward model. It's kind of an autoregressive model. So you feed in input, you output the token, you bring the token back to the input, and you keep on going. And as such, these models are limited computationally, right? So there's something that you can compute with these models and something that you cannot. And therefore, when I give a collection of problems that model can or cannot do, it's not a random collection. There are several tasks that inherently models cannot do. Models cannot do quantitative reasoning well. They cannot do temporal reasoning well. They cannot do aggregation or many other tasks that require maintaining a large intermediate representation and then reasoning on top of it. And of course, they cannot deal with various tasks like logical reasoning and so on, which I'm going to get to. And there is a beginning of understanding today from the computation complexity perspective of what can be computed and what cannot be computed. And some of the limitation, the computational complexity, the limitations of this model. Now, I want to be clear. I'm not saying that we cannot address these kind of problems. I mean, what I'm saying is that we cannot expect that language models on their own will be able to do this reliably. And of course, there's the truth, right? So models cannot tell the difference between truth and things that seem to be true. And in many respects, if you think about it, training of the model encourages them to hallucinate. Because if in the SFT stage, I'm going to give, a question answering data, and I'm going to ask, I don't know, who is the third president of the US? I'm going to give an answer, but I don't know whether the model knows the answer or doesn't know the answer when I do this. So I'm basically encouraging the model to give me an answer, give me a person when you ask about these kind of questions. And here is kind of one of the examples that I want to highlight here. This is a request from the one of the top models to name the top 10 best South Indian restaurants in Philly. And what you get here is that the top one is really a South Indian restaurant in Philly. The next 4 or 5 are South Indian restaurants somewhere, but not in Philly. And the bottom 4, as far as I can say, do not, I can tell, do not exist. But they do look like they could be South Indian. So you know, there are many kinds of hallucinations that we may want to think about, and some of them that have to do with facts. Maybe we should be able to address and at least detect quite reliably, but there are some fundamental reasoning hallucinations, logical consistency and correctness, and so on, that we cannot fix within the model. The only chance we have to do it is, and the reason is that we cannot teach this correctly. We cannot teach models to do things exactly. This needs to be addressed outside the model. And this is really where I want to go now. I want to talk about these kind of tasks. And I'm calling here symbolic reasoning because this is one of the tasks that classical task. It's called Wason selection task. It used to be sort of a classical way to test whether humans are capable of doing logical reasoning. I'm sure many of you have seen this. I'm not going to test you on this, but here's the challenge. You're shown 4 cards. Each one has a number on one face and a color on the other side. You're asked to determine the truth value of the following statement. If a card shows an even number on one face, then its opposite face is blue. And the question is, turn over the minimal number of cards to allow you to determine if the statement is true. And you know, I know that if I give you 30 seconds, you can get it. But the issue is that most people that are not trained in logic or computer science and so on don't get it consistently. However, what's interesting is that if people are given an equivalent test that is grounded in some familiar situation, they get it right. So if you go to, you know, graduate students and you give them an instance like this, if a student scores less than 650 in quantitative GRE tests, they cannot get into a top CS program. I know that today most programs don't want GRE anymore, but you obviously know about it. Yes. And then you give them cards with scores on one side and programs that students are enrolled in the other. People get it with a much higher percentage. Or even simpler, if a student is younger than 21, they cannot buy beer in the US. And then the cards are going to have age on one side and cannot buy beer on the other side. People get it at much higher accuracy. So what's happening here? So what do we learn from the fact that models too can answer questions that were grounded, in fact, kind of like people, but they cannot answer questions by identifying the symbolic structure and doing it consistently. So I think that the world has a symbolic structure. People often, not always, get it. Not always they need to get it. And when they do need to get it, they can use it to reason consistently. Language models cannot get it. But sometimes the token bias produces the same results as if they found it. And then everyone is very impressed and claims that the model can support reasoning. So the second lesson that I want to highlight is that we learned that often token bias is consistent with reasoned conclusions, and we are misled by this. So really the way I think about it is kind of similar to Daniel Kahneman's think fast, think slow. Models perform memorization rather than reasoning. So they think fast. If it's grounded and they've seen something similar, they're going to get it. By thinking slow, we want to identify the structure or the constraints and reason consistently. This must be 100% correct. But the issue is that when we want computer program to support decision making, we need it to be consistent. We need them to identify the structure and be consistent. Imagine what would have happened if your calculator would give you the answer correctly 70% of the time. So, but again, I want to say that there's no surprise here, because if we think about these models, these are inductive learning machines. Inductive learning has some probabilistic guarantees under some assumptions on the examples that it has seen in the past. But sometimes we need exact learning of theories to support, some decisions, and this is something that we do not get for models. So, and again, I want to say there's really no magic here. This is really what kind of theory tells us. And if you think about it, there's been a lot of media about things like alpha geometry and GPT-4o1 that are doing reasoning better, but they are still inductive learning machine. The only tricks that is happening there, and these are impressive tricks and impressive results, is that by additional training that is very focused on specific distribution, on this distribution, models are doing better. But eventually, they cannot do everything correctly, exactly because of the limits. So I want to push a little bit more on this issue of reasoning versus memorization. And I'm going to give this example. This is, again, a Tversky-Kahneman old problem. It's called the Linda problem. That some of you may have seen it. I mean, they used it as a way to look at whether people can understand probability and statistics. Linda is a 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social injustice, and also participated in anti-nuclear demonstration. Which is more probable? One, Linda is a bank teller. Two, Linda is a bank teller and is active in the feminist movement. So, a lot of people would choose 2, even though we know that 2 is a subset of 1. So P is a subset of A, so A is more likely. And models used to make these mistakes too. But over the last few months, models are excellent. In fact, not only they know the answer, they would even tell you, this is Kahneman's and Tversky conjunctive fallacy, and this is the answer. And in fact, it's robust in the sense that, I cannot easily change it. I try to change Linda to Taylor Swift and write a story, or Federer and write a story, and the model still get it. But if I add a little bit more information, we can deceive the model. So here is the way I deceive the model. This worked about 3 weeks ago. I don't know about yesterday. This was the last time I checked it. I start my question by the following request. Write a short paragraph on the greatness of Roger Federer and his accomplishment at Wimbledon. Then answer the following question. Suppose Roger Federer reaches the Wimbledon finals. Which outcome is more likely? A, Federer will lose the first set. B, Federer will lose the first set and win the match. And the model gets it wrong. So I basically added a little bit more context that throughout the reasoning of the model, and we got it wrong. Now, I don't know if maybe today they fix it somehow. They're very, very fast in kind of training. Yeah.
See, Federer is too old. How about, I'm sure he'll lose it. I mean, I've played tennis, so I know. I mean, there's no way he'll get more than us.
No, but we're talking about his history, and the model knows a lot about.
Yeah, but you see, Federer, he plays now.
But this is really the reason the model is misled.
Yeah.
The following story and the fact that they read so much about Federer and his achievement in winning.
Reminds me of SAT, my daughter. So nowadays, I don't know how they try to fool you.
But basically, the lesson here is that still the models do not identify the structure, but rather they memorize and they reach to memory. And in this case, I managed to mislead the way they access it. Okay, I just zoomed it in so you can actually read it more carefully. But again, I want to stress this statement. The world has a symbolic structure. And people often, not always, get it and manage to reason consistently, but models cannot do it. And I want to give one other example, which I find interesting about reasoning versus memorization. So this was constructed in the context of exploring the limitation of reasoning chain. Basically, we developed a new data set that the tests model on the abilities to follow reasoning chains. So you start with an entity, Leonardo DiCaprio in this case, and you go to Wikipedia or DBpedia, and you identify relations that this entity has. In this case, two relations: DiCaprio produced Gardner of Eden and starred in J. Edgar. Now you take one of these entities and you keep on going to DBpedia to identify additional relations. Or before that, I can say that already here I can ask a question, right? I can ask the question, which producer of Gardner of Eden also starred in J. Edgar? Now I can start with J. Edgar and keep on going with this. I'm going to identify two additional relations. So one of them is written by Dustin Black. The second one is produced by Malpaso Productions. And now I have a longer question that I can ask. I can ask which producer of Garden of Eden also starred in a film that was written by Dustin Black and produced by Malpaso Productions. And you can see that I can keep on going this way, which with every entity, I'm going to go and identify relations, and I'm going to ask a question that requires more hops in order to answer. And this is, we know that the model knows all the facts because everything is taken here from Wikipedia. The model has read Wikipedia multiple times, and we can verify that they know them. So now what happens when we test them on the questions? So what you see here are results of multiple models. The colors represent the depth 1, depth 2, up to depth 5 of the questions. And the surprising thing here, well, first of all, is human performance on this task is much, much better than the best model. But the real surprising thing, if you look at it carefully, is that it's relatively flat. That is, it doesn't depend, with the exception of depth 1, which is just an extraction, the performance doesn't depend on the depth, which is surprising, right? You would expect that the deeper the chain, the reasoning chain is, the worse the results. So in order to investigate this better, we were looking at the distance, the semantic distance between the answer and the question. And basically what we draw here is the entity similarity impact on the accuracy. And what you see here, or what you should see here, is a flat line, because if the models are following the reasoning chain, entity similarity should be irrelevant because the knowledge is known, everything is from Wikipedia. However, what we see instead is that we see that entity similarity strongly correlates with performance, which basically means that the model actually memorizes and is influenced by entity similarity. And if you want just concrete example here is an example from the data set, which producer of Garden of Eden also starred in film that was written by Dustin Black and produced by blah, 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 and produced at the end Thunderbolt and Lightfoot in 1974. And the model answers correctly that this was Leonardo DiCaprio. Any idea why? Well, I'm going to take the same question and just change the last spec. Instead of Thunderbolt and Lightfoot in 74, I'm going to make it produce Cook and Bluff in 1968. And now the model answers incorrect. No Leonardo DiCaprio's fan. And the reason is that DiCaprio was born in 74. So when the question mentions 74, it triggers this answer. But when I change it to something else, that the model should know as well, the answer is incorrect. And again, this is just kind of stresses the idea that there is a large focus on memorization rather than identifying the structure and trying to do it. So the third lesson that I'd like to stress is that language models on their own are not as powerful as we thought them. And if we want to use them the way we want to use them, we need to move to systems of models. And the way people think about it today is give a model some agents. And what does that mean? That means that we're going to have multiple models, and they're going to interact with tools that are potentially more reliable, like calculator or analytic tools or productivity tools maybe code interpreters, planners, and so on, and maybe some other expert models. And this is how we're going to kind of make this system of models our new UX, our system. And there are multiple ways of doing that kind of are studied in the literature, and I want to address a couple of them quickly and focus on one of them. So the key one is prompts. I mean, people are very excited about prompting models, and prompting is good. I mean, if you prompt well, you can get sometimes the right answer because you can prompt. By prompting well, it means you're going to give input that the model kind of has seen before. But I want to make sure that we understand that there's no magic here. So people are very excited by chain of thought or by asking questions, think step by step. And it's not the case that once you say, ask the model in the prompt to think step by step, the model says, oh, now you're serious. Okay, so now I'm going to stop and really think more carefully, step by step. Really, it's in the data. And you can actually identify by going to pre-training data. And I'm showing here a website that was identified for me by Yanai Elazar with tens of thousands of examples of math questions where the way it's phrased is, here is a system of equation, think step by step, and here's the solution. Here is factorization, think step by step, here is the solution, and so on. So really, models have seen all these things in training, and now they are triggered by your prompt. And of course, there are many, many other solutions. As I said, in addition to prompts, post-model reasoning, neurosymbolic is something that is coming back to life. Search on top of output of models. I think that query for intermediate factors is something that is going to be bigger and bigger because we know that models cannot reliably support decisions, but they know a lot. So if you want to support decisions, you're able to ask models what could be factors that could influence it. And once you collect all these factors, you can put them into a real reasoning system and get better results. But I want to focus today on this idea of systems of model or augmentation of models via agents, reg, or expert models. Because this is really, first of all, hot. I think there's a lot of potential. And a lot of people think about this, and I want to address some of the difficulties that it says, and perhaps some ideas on how I think we should do it right. So I'm going to start with an example, because our goal is really to support reasoning and support planning. So I can ask you the following question. In torches, in what month of the year is the longest day? And most of you, I think, do not know the answer. But all of you, I think, have a plan for how to derive the answer. And the plan in this case is very simple. All you need to know is where the torches is. And in fact, you don't even know exactly where it is. You just need to know whether it's in northern hemisphere or the southern hemisphere. Now, as I asked you about New York, you don't need a plan. You can just retrieve this information because it's written in many, many places. But the fact that we need a plan to answer questions is happening all the time. If I show you an image and I ask you, when was it taken? Where was it taken? In most cases, you will not know, but it's just a few clicks away, and you can devise a plan that will tell you, that will help you determine the answer to this question. What's important in this image, what's on the signs, what can I learn from it, maybe just a Google search away. Or if you are going to a shopping assistant and you want to buy a charger for the phone, the shopping assistant also has to devise a plan of what kind of question do I have to ask you in order to make sure that I know which phone you have in order to understand how to answer. And this happens all the time when we ask in real world questions. If I want to access a database and I want to answer a question like, who are the female account holders who own credit cards and also have loans? So I have multiple tables and I have to be able to devise a plan of how do I factor this question depending on what tables I have. So this is a very realistic thing. And this is, and it has a lot of application. And you can see dozens of papers coming up every day where people are trying to think about how can we enrich model with this. There is this office bench that tries to address problems like, schedule a team meeting for next Monday at 9 a.m. and send reminder emails to all teammates. And this really involves a plan. and involves touching multiple productivity tools. Or a more recent one, Assistant Bench, that asks questions like, which gym near Tompkins Square Park have fitness classes before 7 a.m. And we already know today that models cannot support this. We don't know how to support it. I mean, the completion rate of this kind of tasks ranges between 16 and 50%, depending on the length of the desired plan. And of course, we want to do more. We want to deal with web agents where there's additional difficulties of where should I click, what should I click, and what should I do after. And even in very, very simple tasks, like, this is kind of, will we make it to dinner before the movie? It's really kind of a Google Maps kind of question. But if you really think about it, it involves a lot more than just Google Maps, because it needs to know, what is the duration of dinner, typical duration of dinner. Do I have time to go to a fancy Japanese restaurant, or do I have to go to Chipotle? What about parking next to the restaurant? So really, there is a need to interact with the model and ask clarification questions, but models don't know how to ask clarification. So LLMs cannot do alone even the simpler tasks.
How can you get the plan?
Okay, that's a key question. You're going to answer it at the end. So we really need to augment the models with the ability to do planning, to interact, to ask clarification questions, and to ground themselves in the external world via this. And again, on their own, LLMs are incapable of addressing tasks that significantly deviate from what they were trained on. So in general, there's really no hope. And I'm going back to there's no magic here. So now, in the literature, you'll see that many people came up with framework. We have, LangChain and LangGraph and, multiple framework for dealing with agents. But the framework are just software engineering frameworks. What you need is to put something into these frameworks. And because this is where the quality is going to determine. We need to think about what does it take to support complex needs, to decompose them, and to orchestrate tools that need to be used in order to do it. And even some basic tasks require routing capabilities. I need to decide which API do I go to, even if it's simple APIs like calculators or productivity tools or analytic tools. And beyond that, we need to decompose the information need and then reason about it. So now you can say, you told us that language models cannot reason, and therefore we need to move out to system of models and deal with agents and so on. But now you're telling us that even in order to go to agents, you need to do some reasoning and some decomposition. So this seems to be kind of cyclic thinking. And you would be right. I mean, this is cyclic thinking. And so what is the answer to this pattern? So I think the answer is that some learning problems are easier than others. And this depends on careful curation of data. So I'll give you an extreme example here of what I mean. So let's assume we know already, and I highlighted earlier, that models cannot be trained reliably to do multiplication. So if I want a model to do 4-digit multiplication, it's very, very difficult to do. If you manage to do something that is close to this, it will not generalize to 7-digit. But it's relatively easy today to train a model to go out to a calculator or to spit out a Python code that will do this 4-digit multiplication reliably, and it will also generalize to 7-digit. So even though this is an extreme example, I think this is the direction we should think about. We should not focus on training the model to do this hard task, but rather we should focus on training translators to go out and do things that other solvers can do reliably. And this doesn't apply only to calculators. I'm going to give some other examples of this. So here is a math word problems of the type that you've done in middle school or something like this. Bobby has 16 toy cars, and the number of cars he has increases by 50% every year. How many toy cars will Bobby have in 3 years? This is taken from the GSM data set. And models get it. Today, I mean, even though the numbers that I've written here are lower, the top model gets it like 90%. But I can perturb this question. I can perturb it, and in this case, I've generated here 5 versions of the same question, changing the numbers, in some cases, changing a little bit of the wording. And in this specific case, this is an extreme case again, only one of these perturbations, the model got correct. This is GPT-4o. Very disappointing. Now, in general, it's not so bad. I mean, the results go by something like 20 to 30%, depending on the model, but still, it indicates that the models cannot do it. Now, there is another path that I can pursue. I can actually take the question, translate it to a Python code. And if I know how to translate it correctly, now I can solve all 5 instances. And of course, it's going to be correct on all 5 of them. So to me, this is the direction we should take, right? So the challenges are, we have to fine-tune models because most decision-making should be done by trainable fine-tune models. The question is, what should we fine-tune? Should we fine-tune the model itself, or should we fine-tune translators? And I think we should fine-tune translators, and this is where code generation, for example, is important. I would even go as far as saying that the reason code generation is important is for this, not so much for helping you code, because there are too many bugs that it just going to take eventually more time from you. And this is true in many, many other domains, as I showed. But of course, it forces us to think about how to curate data so that we can train these translators. We need verifiers in order to curate data, right? We need to be able to know this is the answer to the question. Now, if we have data sets for this, we can do this. And this is really, if you think about it, what Google has done brilliantly in alpha geometry and what they've done with eventually later on with GPT-4o1 and what was mimicked recently with DeepSeek R1. Basically, in some domains where you can get verifiers, you can use this and do it. But this is more general than just math. And I'm going to give a couple of examples that we've played with recently with facilitating reasoning in other domains. So here are 2 questions. These are just question answering domain. Was Gandhi absent from 47 Indian Independence Day celebration? The answer is yes, he was. Was Marie Curie absent from the 1903 Nobel Prize ceremony? The answer is yes, she was absent. And notice that these are the same question, but really the answer is supported by different reasons. In the first case, he was just in a different place and it was documented. In the second case, Marie Curie was not allowed to participate because in 1903, females were not allowed to participate in Nobel Prize ceremonies. But you can ask exactly the same question again. Was Bruce Lee absent from the 1964 University of Washington graduation ceremony? And in this case, the model answers incorrect, even though we know that the model knows all the components of the answer. So what's happening here? Exactly the same phenomenon as before. Bruce Lee together with University of Washington, these are 2 entities that don't appear a lot often. So the memorization ability, the token bias of the model doesn't kick in and we get it wrong. So what can we do? And I'm going back to the procedure that I kind of suggested before, and I'm going to make it a little bit more formal. I want to learn the symbolic process that guides this reason. I want to transfer what the LLM do well, answer some of the questions, to a symbolic process which can again be applied to solve what models cannot do well. And then again, why symbolic process? Because this is the only way that we're going to guarantee consistent reasoning. So the methodology here is what I call incidental supervision for code generating agents. I'm going to generate simple example based on the problems that the model can answer well. Via abstraction, divide and conquer, I'm going to abstract these problems a little bit. And then I'm going to use a separate model to learn Python code that solves this problem. Once I do this, I can go back to my base model with these pairs, simple problem, comma, Python code, and train this model. So here is how it's going to work. I'm going to start with this Bruce Lee example. I'm going to abstract it. Was person A absent from event B? And I'm going to find instances in my data set that are similar to this. Gandhi is one example. Was Barack Obama absent from the 1961 inauguration ceremony? Yes, he was. He was He was just born that year. And then I can generate the code for this. It's going to be different code for this problem, but I can generate reliably or relatively reliably this code. And this is really self-supervision, right? Because I don't need human annotation in order to do this. And once I have this code, I can go back and run it on examples that I wasn't able to do before. And this results in significant improvement in the reasoning ability because I've abstracted. So how do we think about it? So you can think about what we've done here as teaching the model to solve the easy problems the right way via the symbolic program. And therefore, they can solve also the hard problem the right way. Or you can think about it as a way to exploit the model's ability to memorize, only that we force them not to memorize the entities, kind of the shell of features, but rather memorize the reasoning path rather than the tokens. And I'm not sure exactly what's the best way. I mean, we'll have to move some more forward in order to understand what's important. So I want to finish with saying that, reasoning is really not an abstract notion. This is something that is really important in many, many tasks, from visual perception and access to databases. And I'm going to give quickly just a few examples that are from this domain. So one of them is this visual reasoning thing. I mean, hopefully you can be impressed with the example on the left here, a bear eating salmon. This is a true response from stability, from stable diffusion. But in general, models that, again, we are very, very impressed with visual processing models, but they are not so good. And you have to think about how to supervise this model with enriched data or augment them with expert agents so that we can make them more reliable. For example, if I ask top models, which point on the right corresponds to point 1 on the left? Models cannot get it right. Humans get it 100%. If I ask questions about depth, which point is closer to the camera, A or B? People get it 100%. Models do not get it. And there's a lot of problems like that with models. And I'm giving here a collection of other problems, that involve visual perception, but also some reasoning. And it turns out that you can develop what we call here a visual sketchpad, which is basically the same idea. Go to specific tools in order to either augment the image or solve, depth from perception and so on, and give this to the model. And now the model will support your visual tasks in a better way. And similar issues come up in the very, very important problems of RAG, retrieval augmented generation, which to me is one of the key, if not the key use case of language models. People forget sometimes that RAG has an R in it, and the R actually isn't working, despite what's written in the newspaper. So I'm going to give an example. So if I want to access databases and want to ask a question that I asked before, who are the female account holders who own credit cards and also have loans? So this is an easy question if there is a single table that is sufficient to answer the question, because then I can just translate this natural language expression into a SQL expression, done. It's also an okay question if the query corresponds to how the information is organized in the database. But most people that go to ask questions to knowledge bases or databases have no clue how the database is organized. So typically, what will be the general case is that the query will not align with how the information is organized. So really, in order to understand how to access it, how to decompose the question, and consequently, how to translate it to a SQL expression, I need to do a lot more work. And this is where the results drop quite significantly. So really, I need to understand the data organization process, which models cannot do, and I have to do something else. And there's research on this. I mean, I'm going to mention here a couple of research that basically suggest two different solutions. One of them is training time solution, and another one is inference runtime solution that essentially is doing some kind of constraint optimization on top of the possibilities of how to break down this query And I'm not going to go into the details. I'm just going to say that this is really important because there's a lot of data out there, a lot of tables out there, a lot of charts and graphs out there that we want to be able to access reliably, aggregate information from, reason on top of them, and even the access is not so simple. So I'm going to stop here and just conclude. I mean, I think we all agree that LLMs are making big waves, and for the right reasons, because the technology is really impressive and can do a lot of things, especially on the generations side, where we don't necessarily care so much if it's completely accurate. We just look at it, be impressed with it, modify it a little bit, and move on in many, many applications. But when we care about decision making, this isn't the case. And if we want to push this decision-making ability, we really need to move out of relying on single models, and we need to do a lot more in order to do it. And we also need to do a lot more in order to restrain the models. I didn't talk about this today, but clearly a very important area. And I abstracted my presentation here into 3 lessons. I mean, the first lesson is what we've learned about why the models are so powerful and so impressive. The second one has to do with understanding that memorization is misleading us. And the third one is understanding that models themselves are not going to solve all the world's problems. We have to figure out how to use them and build on top of them in order to do much better. And I'm going to stop here and thank you.
There's lots of time for questions. Why don't we take a couple questions from the room, and then anyone that wants to raise your hand on Zoom, I can go ahead.
Yeah, thank you for the presentation. Wonderful presentation. I'm kind of confused with when you said the translator version of like the way we should think about the translators as scientifically translated. I've heard some LRM talks, like large reasoning model talks, where they actually say that the models are doing that reasoning. The models are breaking the big problem into small pieces, and they are like internally trying to get the best answer for each of the smaller questions and combining them to give like this, especially with O1 and the
Yeah, and they are doing it, right? So if you form the model properly, it will break down the questions and it will try to solve each one of them. But what is happening with O1? Let me just say so. O1 basically does that and basically suggests a lot of optional solutions. And because you know the answer, training time, you can actually do reinforcement learning back from the solution and train the model to better explore this space of possible solutions. But at the end, you just train the model. So it's a machine learning model that was trained on distribution that better fits the collection of questions that you care about. And it's going to do on this kind of question much better than without it. Will it solve satisfiability? No, it will not solve satisfiability. Because it cannot. I mean, this is still a feed-forward model, and it's an n-cube model, and it cannot solve a computationally hard problem. That's it. You can train it to approximate it, and it will do well on the distribution that you train on, because it's a very, very large model. The distribution can cover a lot of cases, but it will not do the reasoning. It will never compete with what exact solvers can do. And the translation thing that I alluded to means that, perhaps, and in fact, I don't have the computational complexity results on this, but this is still in exploration. A better way would be to rely on solvers to solve the really hard problems and try to train models to access solvers correctly, rather than try to directly solve the problem.
Okay, hi, Professor. I got a question. So you mentioned that currently the largest models do memorization rather than like reasoning. And you mentioned that we can somehow alleviate this issue with agents, but it seems that we cannot really solve this problem with the agent. So what do you think that might be the ultimate way to empower the large language models with reasoning ability?
So, well, two things. First of all, maybe I don't want to short sell memorization because it's a very sophisticated memorization. You have very sophisticated and deep similarity function. So they can access a lot of information and do abstraction. It's after all a machine learning model. But you're right. I mean, they cannot solve these hard problems. And I wouldn't say that we should try to alleviate these difficulties. We should try to take a detour and basically, rather than count on the model to solve the reasoning problem or the planning problem, figure out a way to reliably go outside of the model and use solvers that can do that. So the calculator example that I've given, that all the top models are already using, is a good example for that, right? So don't try to do the multiplication in the model, but rather try to translate your problem into an input to a solver. We can do this also with planners. We can do this also with other constraint optimization problems or solvers. And how to do this reliably, it's still a challenge. Yeah.
Yeah, I have a question. I like very much your talk. Another way to do what you're saying, which we do right now, vision, is we put, for example, a differential equation in the latent space. So we are forcing it to think an abstract. Or in medical domain, what we do is, if there is some knowledge, because the data can never tell you what is you harm and why. There's no way they can check to the level of the doctor. So what we do is we input domain knowledge in the latent space. Then, so one way is instead of going outside with all this, maybe put them inside so you can augment the thing, but you have to understand the latent space.
I think that will push the boundaries of what problems you can solve, because it's similar to me to the O1 case, where you basically provide the model with a more concrete distribution of what you care about, but it will not solve the problem. Yeah, I mean, if maybe you don't want to solve the problem, you just want to solve this problem.
Also,
and then you can
generic problems if I put more abstraction, but in the like so going outside.
Again, I think that you're still limited by the computational power of the model. So there's some things you can solve this way and some things you cannot. Yeah.
Do you have like some insight into why it would be harder in general to produce a solution versus generating queries to produce a solution? Some queries are actually pretty hard to.
Yeah, okay, it's a very good question. No, that's the short answer. I mean, I'm very interested in trying to figure it out. If people have any insight, I'm interested in discussing it. I think that these problems are easier computationally, but I don't have a clue for it. Experimentally, it looks like it, but no deeper thought than that as of yet. Yeah.
Thank you very much. A really nice talk. Near the beginning, you said AGI is not coming, and I wonder. I think I agree, but I also there's a lot of smart people who just seem to disagree with that. I wonder if you can say why you think that.
Oh, I thought that you were going to ask why they think that. That's easier. I'm going to call it AGI, where the model comes down off my desk on the second floor, goes down to the kitchen, bring me a slice of cake. That's going to be closer to AGI. I think that we are very, very far, because that will require us to do a lot more things in other domains than reading text or even looking in images. And I think we have time. Yeah, go ahead.
A couple of years ago, there was a book called The Method of AI by Ed Larson. Women argued that the main problem with AI is the lack of productive. Funny thing is, years later, ChatGPT is very well reasoning, given tools and knowledge from internet. And in terms of inductive reasoning, would be month ago is on par with human, or even better than human art challenge, which is very hard inductive puzzles. And for inductive reasoning, we know that AI, long time ago, I understand that these are not solved problems, but in terms of the main categories of reasoning, where are the challenges exactly? Which of these other which of these are really the challenge now? Challenge.
Okay, so you put a lot of terminology there, and it's inductive reasoning to me is a misnomer. It's not reasoning. Okay, so that's my definition. There's induction, and models are doing induction very well. They've been trained on a lot of examples, and under strong probabilistic assumptions, they're going to do very well on the same distribution. They will not solve arc problems that are different enough from arc problems that they've seen. And I've shown this on GSM. You can take all these problems and perturb them enough, and you will see a significant drop in the results of the models. And this applies to all these data sets and all the models. O1, R1, I haven't tried all three, but I bet it's going to be the same thing. Maybe we'll just have to do a little bit more work in order to show this, because they're not doing reasoning, they're doing induction, they're doing it very well. Now, I do agree with you about abduction, because abduction is basically going back to an explanation. Given an observation, what could explain it? And models know a lot of stuff. And therefore, in many, many situations, that could give you plausible explanation for this. And if you're able to use it somehow in your decision-making process, I think it's going to help. So I do agree that models can support abduction well. Now, all this issue of they're doing better than humans, that's meaningless to me. Of course, they're going to do better than humans on Math Olympiads, because they've read all the Math Olympiads going back to whenever it started many, many times, and you haven't. And it's to me, this is meaningless. It shows that they are strong inductive learning machines, but and by the way, they will be able to develop optional solutions for these kind of problems much faster than you can. But my calculator is doing a 4-digit multiplication much faster than I can. I don't think that this is an indication that we are close to AGI any more than 2 years ago. Yeah.
I couldn't agree more with what you said, and agree with everything that you said in this talk. But I have a hard question, which is to sort of situate what you're saying in the larger social context of the world that we live in, the scarce resources that we have, the problems that we need to solve, the way that the general public doesn't get to decide which things they want and which they don't. I fully believe that reasoning models augmented by certain kinds of agents or retrieval systems can solve some big problems, we hope, pharmacological, perhaps mathematical, etc. I give faith to that. I somewhat believe that they might produce a reliable-ish personal assistant at great cost, but not necessarily a better system or even as good a system, and certainly not as efficient a system as would be a hard engineered system for doing certain tasks like booking a restaurant and so forth. So my question is that you seem to me to have shown something that I think a lot of people already know, which is that large language models are white elephants. They absorb an enormous amount of resources to do things that are impressive, but that have relatively little utility. And now we're trying to like push every nook and cranny and to make these into hybrid white elephants without identifying in advance, what are the utilities that we really want? Because we don't have forever and we don't have infinite resources. And we have a lot of people making decisions for us who are not great decision makers. And I think I trust you more.
I don't disagree with what you said. I think sort of the what they call in industry the return on investment is still an open question. Clearly, a lot of people are playing with the models and are using them to write, graduate school essays. And
very bad ones. Let me say that in this room. Very bad graduate school
they feel
essays.
that it saved their time, and many other kind of generation-like things. People feel that they are useful and they help them. Even in that, I think that there's some risks because sometimes models hallucinate. I have personal stories about this. But you're right. I mean, whether companies eventually are going to use it and make money from it is questionable. However, I think that you should give some companies at least more credit than you do, and they will resort to a mix of engineering solutions and models in order to develop reliable solutions. They will not just say, oh, I read in the newspaper that someone said that these models are capable, and therefore I'm going to give a solution. They will engineer it to that. Is the ROI going to be positive or not? I don't know.
Yeah. Is there a problem that you could mention that these methods will be able to do something more than what we know in complexity?
I didn't get
Let's say any NP-hard problem. Pick any, and maybe there's a collection of instances for which this method will be helpful.
Well,
is there any problem in your mind that you say, oh yeah, work that one, we have a chance?
they will not solve NPR problem.
No, I understand, but it may be a very large collection of instances for
Yeah,
which this method could
I
help.
think they already do. Yeah, I think, if you go to satisfiability competition today, you will see that machine learning methods are solving, I don't know exactly what the number is today, but maybe 80% of the instances, much better than the hard methods, the methods with guarantee. Just because, they're similar enough under some notion of similarity to things in the training data. Maybe this 80% is good enough for you for a lot of practical application. Maybe not. So it really depends on you. And in this sense, yeah, I mean, people can solve maybe logistics problems this way because they care about a narrow slice of this. But again, this is going back to Lauren's questions about the engineering solution. People will engineering to that and find that they don't care about everything. They care about this. And for this, they can engineer the model to do what they want. I think this is going to happen.
There's a question from the remote participants. Mark, do you want to unmute and just ask?
Can you do it?
No.
You got the answer.
So Mark Simon says you referred multiple times to using LLMs for what they know, but also that a lot of apparent knowledge is explainable as token bias, beyond which LLMs remain stochastic, so that even token bias does not seem to be reliable. How then do we know what LLMs know? Or is it just that LLMs know how to be linguistically fluent?
Okay, first of all, they do know how to be linguistic. That's clear. It's not so easy to know what they know. I mean, there's a lot of work on this, and people have methods to kind of figure out. Sometimes it's costly because it requires to run models multiple times and to look at consistency and so on. But I think we have okay methods today to know what models know. But we have to understand that, okay, this is another kind of area that I didn't get to talk about at all, but I'm very interested in. Even the data that is out there, the data models were trained on, and the data models see in their context when you give it to them or in reg, the data is inconsistent. For many reasons, it's inconsistent. Sometimes for temporal reasons. Sometimes because legitimately, there are multiple perspectives on things. And sometimes there are conflicts in the data. And when there are conflicts in the data, as I've shown in the first example, we actually have no clue what the models will do. So you're right. I mean, we are using too easily the notion of the models know, but we should put quotes around it, because that in itself is an interesting issue. And there's beginning of research in this direction of how to deal with conflicting information in the input and conflicting information in the output.
Thank you for the talk. Regarding the orchestration of specialized agents, it occurs to me the most natural way to develop such an agent would be to tune a language model. Does that sort of create another maybe problem of if the problem is that the models haven't been trained for this particular task, that would solve it. But if the problem is that the model doesn't encode the right information, might that just sort of lead to another layer of hallucination, if you will?
Yes, so I think the word agent is a little bit too loaded. And the question is, what do you mean here? So to me, the basic problems, or the basic two problems in the agents technology is, one is routing. So given information need in natural language, I have to decide which API do I go to. And I often will have 200 options. And then I have to have a router, and this could be a language model, but it could also be maybe a special purpose model that I train in order to decide which of the APIs that I have is intended here, one, and two, how to go to this API. What should I send this API? Do I have all the information that I need to send to this API? Some of these things, yeah, you can do it with language models. You can do it well with good language models if you don't have too many options. You cannot do it well today if you have too many options or the APIs are complex enough and so on. And once you have multiple steps, it breaks down very quickly. This is the 16% that I cited on task completion. If you have, say, more than 4 steps that you have to do, it dies. So I think just general purpose language models are not going to carry. Question there?
Yeah, a little bit more in the weeds than the other questions. So when you talk about the retrieval task, where they write Python programs to do the task,
What's the baseline you're comparing that again? Is it, do you give them an actual like code runner to let them run this code, or do you give them an interpreter? Or do you just say, write the code and use it to train them and give them the Python code and say,
You mean when I did the QA thing?
yeah.
Okay, so I do in this specific case, we gave them the Python code. We also verified manually on a sample how good the Python code was. And I think the answer was something like between 70 and 80% of the Python was correct. And so basically what you're doing is you're training a model with noisy data. Is it good enough or not? It's better than without it.
How different is this than traditional train of thought, right? Where you just give them the reasoning and, let them go through the reasoning? Is it a very formal way of expressing the reasoning, or is it something more than that?
Oh, I think the very formal way is a big difference.
So we're just saying it's a very formal way of expressing your chain of thought. We're not actually augmenting it with an interpreter and saying, let's actually run the Python code in some database and find out. We're just saying, express your thought very clearly, and that in and of itself shows
That's
some result.
that's
Okay, thank you.
You move to a formal solver if you want. Yeah.
Thank
you.
Don't you think like agents are more like phone jobs with some reasoning and adaptability?
So again, agent is a loaded word. A calculator could be an agent. A constraint optimization solver could be an agent. An API or someone that knows how to code an API could be an agent. So an agent is not necessarily a model, a machine learning model. So the question is, what do you mean when you say agent? And the truth is that you're going to have a range of things that we are going to call agents.
So your notion of augmentation is, okay, you use the agent, but the model is still not verified.
Well, so what I want the model to be able to do in this case is to produce reliable calls to external, let's call them programs. Some of them are going to be models themselves. Some of them are going to be, deterministic solvers. But I want to make sure that my model knows how to call them well. Well, how to decide which one to call and then how to call them well. And I think this is a little bit easier than trying to solve the ultimate final.
We're trying in Vision to integrate those into the model so we improve the model. But my experience with this model is they, unfortunately, is like image processing computer vision. Image processing, you deal at the pixels level. So they memorize the tokens, etc., but it's not the right representation. So what we're trying to do is transform the latent space to another base of abstraction, the way humans. If we evolved over, millennia, is because of this abstraction, and language is an abstraction of the real world, right?
Okay.
So that's what we're trying to do.
Yeah, and maybe this is going to solve a lot of your problems, but still, I think that so for example, in vision, there are some problems that we already know that we can train a standalone machine learning based model, and it will solve it. Simple one. And why not give the model, the LLM, the ability to use these simple ones as modules? It will just make them more powerful.
We're trying to make more inference, like use the language in.
Yeah, I'm not saying it's the only way.
I'm just saying this.
But that's one way that I think is powerful. This is the sketchbed here is one example.
So I think we're coming up to time. So that's thanks, Dan, again.